Do I have a pointer?
Yes, I can give you one.
So today I'm going to give you two lectures. The first one is the tunability. Tunability means the various type of physical property we can tune by using the variety of methods. The first I'm going to talk about the wavelength tunability. That is the most important for plastic crystal. So we can use various type of method. One is, of course, corrosive pitch can, sorry. So anyway, what we should do is changing the helical pitch. If we can change the helical pitch, we can tune the wavelengths of lasing. So the first I will show you by changing temperature, we can tune. And the other one is the mechanical tuning, and the electric field tuning, and photo tuning, and spatial tuning. Spatial tuning means the position-dependent tuning. And also, finally, I will tell you the multi-mode laser. And for the polarization of light, we can easily change. If your lasing light is polarized, then we can tune by passing through the pneumatic layer. So we can change the phase so that we can easily get circularly polarized light, linearly polarized light, and so on. And we also be able to tune the direction. I will tell you two kind of method. One is the phase-induced tuning, and the other one is the omnidirectional lasing. So we can laze to all the direction. So that's the story of my first lecture. Okay, first, thermal tuning. This is very previous old data. By changing temperature, the lasing wavelengths changes. Looks like continuously change. However, this is not true because, of course, the helical pitch changes with temperature. However, the situation is that the surface, the molecule are fixed at surface. So the pitch cannot change continuously. That means that we always have the integer and half integer number of pitches inside the cell. So if we have the 10 pitches, then by changing temperature, we will have 10 and a half pitch, or like this. So this is the data by Funamoto et al. They changed the temperature, so they showed the band edge wavelengths changes discontinuously, like this. So these, the closed square shows the result of 9 micrometer. And if you look at the thicker cell, the changing rate is much smaller than in this case. So in this case, from the simple calculation, considering what I said before, by using the experimental condition, we can suggest that the 12.3 12.3 nanometer is the interval. So actually, experimentally, they observed the changing all the 12 nanometer, like this. So lasing also occurs discontinuously, like this. So at this point, for instance, since at the lasing excitation spot, there are two pitch regions, so the simultaneous lasing at two wavelengths occurs. So this is the most simple thermal tuning. And the other interesting tuning way is it is also the thermal tuning. However, in this case, these also use the chiral dopant, which depend. Okay, so the solubility of chiral dopant is temperature dependent. So, for instance, if we did increase the temperature, then the solubility of chiral dopant increase, so the pitch decreased. This is the result. By increasing temperature, the pitch becomes shorter, so the lasing wavelengths can be tuned in this wavelength range. So if you use the two-die system, you can extend the tunable range more. So this is the interesting method too. And now I will, this is also a very famous paper using the Lastima. This group used the didoped Lastima. So by extending the Lastima film, then the film becomes thinner, so that since the molecular orientation of the surface is fixed, so the pitch becomes shorter. So the lowest extension you have red, and by extending the film becomes thinner, so the red changes to green and blue. And they also observe the lasing at each wavelength. So this is one of the applications when you use the Lastima as a acoustic host. Okay, we can also tune the pitch by applying the electric field. If your helical axis is perpendicular to the surface, since the surface, the molecular orientation is fixed, so it's not easy to continuously change the pitch. However, if you use such kind of cell, the helical pitch is parallel to the substrate. In this case, we can very easily change the pitch by applying an electric field. So these people use this kind of cell, and of course the lasing occurs to this direction. And they succeeded in getting a lasing wavelength changes with applied electric field like this. Although the tuning range is not so wide. Okay, the other method for tuning is the orientational change of pneumatic liquid crystal between the recursive liquid crystal. By inserting the pneumatic liquid crystal, didoped pneumatic liquid crystal, we have the defect mode lasing like this, as I explained yesterday. Then by applying the field, the pneumatic orientation changes so that the effective the thickness, optical thickness changes. So the lasing peak changes like this within the photonic band gap. So still in this case, the tunable range is very short. It is confined in the photonic band region. Okay. The another interesting application is light. Okay, light irradiation. I introduced two papers. These two papers. In this case, phototransformation in optically active chiral molecule is possible, although it is irreversible process. So by the shining light, the transformation occurs, then the pitch changes like this. And this is more interesting by Flumi. They use the photolysis reaction of recursive iodine in recursive liquid crystal. In this case, tunable range is very wide, 600 to almost 700. So they succeeded in tuning quite wide range by using the irradiation of ultraviolet light. So this change is as increasing the irradiation time, irradiation energy. So, okay, so, but still we cannot tune the wavelengths over a full visible range. So we try to tune the lasing action over a full visible range using the polymer classic liquid crystal. So before our work, mainly two groups are involved in the spatial tuning. The first, the Chan-Sidley et al. Reported that introduction of pitch gradient using two classic liquid crystals with different pitches, then the position sensitive lasing occurs over 50 nanometer. But tunable range is still 50 nanometer. But then after this work, they also reported the position sensitive lasing over full visible region. However, in this case, there is the small window, 50 nanometer range they couldn't raise. And moreover, in their case, they use 6 dyes, many dyes. And the other group, Wang et al., reported the different method. They introduced a pitch gradient due to temperature gradient. So they introduce a temperature gradient to the cell so that the pitch changes with depending on the temperature. And by this method, they made some range, some tunable range. They attained the tunable range. However, and also they polymerize the structure to stabilize the structure. In this case, they do not use the polymer. So after several hours or days, the gradient disappears. But in this case, polymerization was made. However, the available tunable range was only 50 nanometer. So still, they did not succeed in the lasing over full visible range. So we tried. We use two dye, coumarin and DCM, because to tune the lasing wavelengths over a full visible region, the emission spectrum must cover all the visible region. In this case, this blue line is the data of coumarin. So this is absorption of coumarin, this is the emission of coumarin, and this is the absorption of DCM and emission of DCM. So from 450 or 60 to almost 700, the two emission curves. So since we use if you look at the emission absorption of DCM and emission of coumarin, this overlap in quite wide wavelength range. So we can expect the energy transfer from the coumarin to DCM. So by exciting coumarin, we can also get the emission from DCM through this energy transfer. So what we did is this way. We made the empty cell, and we introduced the short pitch liquid crystal with coumarin from this side, and we introduced the long pitch crystalline liquid crystal with coumarin and DCM. Then we made a contact cell. After waiting several minutes or hours, we can form a pitch gradient like this. So pitch is shorter here and longer here. And DCM, also DCM has a gradient like this, and coumarin has also a gradient this way. So if we excite here, then the coumarin, here is the coumarin concentration is larger compared to DCM, so the coumarin emit light. But in this region, the transfer from coumarin to DCM occurs, and DCM emit light. So, so this is the okay. So this is the result. This is the position-dependent reflection spectrum. Reflection spectrum changes the positionally, and also the lasing occurs at each lower energy edge. So the emission, we observe the emission from 470 to 670 over 200 nanometer we can laze. So this is the real image. So if we excite the left-hand side, we can laze the blue emission, and from the middle we have green, and from the right we have red lasing emission. So then the next we have to do is the polarization. It doesn't work. So so far the result is still a low molecular weight liquid crystal. So after, for instance, one day the gradient disappears. So we use the photocurable molecules to stabilize their structure. So we use these kind of the mixture of the photocurable molecules. Then this is the real cell, the photograph of real cell. You can see a line here. This is the discontinuous change of the pitch, as I mentioned before. But you see a very clear change of the pitch from the red side to blue side can be obtained. And by polymerization, the pitch becomes a little bit shorter. However, after a few months, it is stable. And lasing also occurs in the photovisible region. So this is one of the promising the application. We can make a dye-doped classic liquid crystal polymer film, and by changing the excitation position, we can raise any wavelengths of light. The other topic is multi-mode lasing. I already said that classic liquid crystal exhibit a photonic band gap at the wavelengths corresponding to the optical pitch. So this pitch is in green region, then only the green light is reflected. However, we made the white light reflector by using the classic liquid crystal with single pitch. So the question is, can we make multi-photonic bands or a wide photonic band using a single pitch classic liquid crystals? The answer is yes. I will tell you RGB white light reflector, also a simultaneous RGB lasing using a single pitch classic liquid crystal. We only use the classic liquid crystal with pitch of green light. However, we can make a multi-band reflector. So how can we make? What's the structure? Okay, so first I will show you the simulation. This is the classic, and the classic with 1 pitch thick and 5 pitch thick. Then the reflection bands changes like this. If the thickness is very thin, then the classic reflectance is low, but the band width becomes very large. Okay. Then with increasing the thickness, the stop band or the photonic band becomes sharp and strong. So this is the result. We can make a blue, green, red multi-band structure by using this kind of structure. So we keep the thickness of classic very thin, like 1 pitch or 1.5 pitch. But we insert a PVA layer in each classic structure. So this PVA acts as the defect for this classic structure, and also PVA is important to align next classic liquid crystal. So by spin coating PVA on this polymer classic liquid crystal, we spin coat the another classic liquid crystal. Then we can form a very well defined the structure of the classic liquid crystal. So let me show you the comparison between the experiment and calculation. So this is the result. In this case, we use classic liquid crystal with 1.5 pitch. And thickness of PVA is 0.35 micrometer. And with increasing the number of classic liquid crystal, layer, the reflectance becomes large. And this is the calculation. You see a very good agreement between the experiment and calculation. This is the another case if we use cholesteric, the 2 pitch thickness, and this case cholesteric with 5 pitch thickness. In this case, these multiband position becomes shrink like this, and becomes the single band, almost single band. So in this case, for instance, the reflectance is located almost in the white region in the color diagram. So we can make a white light reflector in this way. We can also use this kind of structure for the liquid crystal lasing. So before that, I want to emphasize the how well defined the cholesteric structure. This is the fitted result. We fitted the experimental. We fitted the experimental result by calculation. Then we obtained the thickness of cholesteric liquid crystal and PVA thickness and so forth. And this is the measured result. The result, the agreement is quite good. So this table shows how we can control the thickness of the cholesteric liquid crystal and pitch of the cholesteric liquid crystal. Okay, the another application is lasing. By using the cholesteric liquid crystal large cholesteric liquid crystal system, as I mentioned, and by sandwiching the didoped nematic liquid crystal by this cholesteric liquid crystal film, we can make merge mode lasing. In this case, we also use coumarin and DCM, the mixed dye system. And I just tell you the result. For instance, this one, with increasing the excitation, the power, finally we can lace RGB simultaneous lasing. These peak located here, red, green, and blue. So we can make the RGB simultaneous lasing. Okay.
We'll go an extra 5 minutes.
Oh, okay. So I just briefly tell you the polarization tuning. This is a different system. We do not use cholesteric liquid crystal. Instead, we use the one-dimensional grating made by polymer. Okay. In this case, and the didoped nematic liquid crystal is located here. And by using the diffraction, the emission is directed to the normal direction. And in this case, we have TE mode this direction. And by applying the electric field, the nematic change the orientation so that we can tune the phase difference, okay, by talking to the nematic liquid crystal. So we can tune the polarization like this. I will show you the result. By changing the field, we can lace right-handed polarization and TM modes TE modes or left-handed polarized light. The degree of polarization is quite good if you look at this small, the peak. So this is the, we can apply this method to concept liquid crystal laser too. Okay, this is maybe too much. I will skip this. This is omnidirectional lasing using the Helfrich effect. So I'll skip this. Oh, okay. This is the last one. Yeah.
Okay,
I think, yeah,
okay,
I just stop here.
All right. Questions? Any questions from? Yes.
As far as I understood, you made it from the old light. Why? Yeah. What's the main reason that it's not in industry yet? Because it seems very.
Yeah, in this case, okay, if we do not apply field, the cholesteric helical axis is along this direction. Okay, so if we observe the normal direction, we have a strong peak here, lasing peak here. But we observe this lasing from the oblique direction, then the peak intensity decreases like this. However, by applying the field, this is our interpretation. A kind of electrodynamics occurs. It's a Helfrich effect. So cholesteric pitch direction is modulated like this. So pitch direction changes from this direction to this direction, so forth. So in this case, the lasing action always occurs along the helical axis. So in this case, by looking at from 1 degree to large angle, we always see the same lasing emission. So that is the reason. Sometimes the people misunderstood because by applying the field, the cholesteric reflection color changes from the normal direction, so that they realize that they can tune the pitch. However, it's not true. The main reason could be this kind of Helfrich effect, because this is very clear.
So if you do this, do you also observe that the wavelength is shifting a little bit, right? Because depending on whether you have normal incidence or oblique, you collect light at oblique angle.
But in this case, pitch doesn't change. It doesn't change. That's just the direction, the helical axis changes. So the pitch doesn't change.
Is there more questions? Can we think today out here? 10 minutes for the break. Back here at 25.